Hi, this is an introduction to the oscilloscope. This is going to be the primary instrument that you'll be using in this lab to take your measurements. So the oscilloscope is a little different from the DMM because it visually shows you the change in voltage rather than just giving you a single value. So first, when you turn on your oscilloscope, it's a good thing to know where your zero is. It's pretty arbitrary where this line is as long as you know your divisions. For simplicity's sake, we'll just have 0 at the center. And you would change the position of this line by adjusting this smaller knob. And since we're on channel 1, which is yellow, we'll use the channel 1 controls right here. So we can raise that up to 0. Alternatively, you can always hit the auto set button. However, sometimes I'll zoom into a trace that is small part of your signal or too large a part of your signal, and it won't give you the part that you're actually looking for. So it's always good to know what you're looking for so you can manually find it if auto set does not work. So first thing we're going to do is we're going to take a look at just a DC signal that is roughly 24 volts. And we're going to connect the BNC cable right here to channel 1, and then the other end to BNC mini grabbers. So right now the signal is off the screen, and this will happen a lot. So the first thing you want to check is right here. It will show you your divisions, which means from each line that is 5 volts, and we can change that scale by adjusting this larger knob. So if I want to decrease it, it'll go to 2, and that's 2, 4, 6, 8, etc. So right now this scope can only go to 5 volts for if you're just measuring directly with the mini grabbers. So if we lower this down so our 0 is at this division, we will see it come up here. But now we know that the middle reference is no longer 0. We moved our 0 down here. So if we go 5, 10, 15, 20, 25, and 26, right? So that is giving us the correct reading. In this lab, you may be using a probe to measure higher voltages, and this is also a BNC connector, and you're just going to connect it directly into the oscilloscope. And notice how I plugged in channel 2, and to bring up the channel 2 signal, you're just going to hit this once, and we have the noisy signal here. And the divisions for channel 2 are going to be different from channel 1 and etc. for the other channels. So this one for channel 2 is at 20 millivolts, while channel 1 is at 5 volts per division. So for this purpose, we're going to match the divisions. So I'm going to bring this up to 5 volts as well. And this is at 0, and since it's not connected to anything, we expect it to be 0. So what the probe does is it can take a high voltage signal and properly display on the oscilloscope, whereas, as we saw before, if each division is only 5 volts, there's going to be a max ceiling for what the mini grabbers can measure. So the probe has the option to go to times 10 measurements, which means it'll take whatever actual measurement or actual voltage that you're measuring, and then it'll divide it by 10. So if we go to times 10 here and connect it to the same 24 volt supply, we would expect to see a 2.4 volt display. Or in this case, 2.6, since it's a little off. So we take the probe and we'll attach it back to our 26 volt power supply. The small grabber will always be your ground or negative, which is equivalent to the black mini grabber. And the larger clip will be your positive, or the red one. So if we go back to the oscilloscope and we pull up our signal for channel 2, we want to put our scale to match channel 1 so we can compare the two. So if we have it at 5 volts per division and we match our zeros roughly, we'll see that this is displaying 2.6 volts, which is as expected, but we're measuring a 26 volt power supply. And to correct for that, you're going to want to pull up the probe attenuation menu by tapping the channel button once, which will bring up the menu. And to probe setup, we're at 1 times. So click the corresponding button below, and we'll just set it to times 10 attenuation. And then you see the attenuation up there changed, and then we'll pull off our menu, and we will bring it back down to 5 volts, because when we change the times 10 attenuation, this changed to 50 volts per division, so you want to be careful of what your divisions are when you're changing your settings. So back at 5 volts, now we see that it's displaying the proper signal. So what happened is we have our 26 volt power supply getting divided by our probe to display 2.6 volts, and then having our oscilloscope multiply that signal again by 10. So while this is just a demonstration to compare with the mini grabbers, if you have a larger signal that is out of range of the machine and you can't you can't measure it directly with the mini grabbers to show your signal, you have to be aware of what you're doing and what settings you have it on to display a proper signal. So next, we want to examine the AC coupled signal setting, and we will remove our second channel because we're done with the probe, and you can remove your signal by hitting the button twice, and then our blue signal's gone, and we can remove our probe. If we want to bring up the menu for channel 1 again, and we want to focus on the coupling, right now it's on DC coupling, which means it's showing the DC signal that this oscilloscope is reading. And we want to look at AC coupling, which means that the instrument is ignoring the DC voltage. So as you see, it brought it back to our set 0 down here. So while we're connected to 26 volts, it's only it's showing 0. And if you look over here, the little sine wave signal symbolizes AC current. And what this can tell us is it shows the AC signal riding on top of a DC signal. So it negates the 5 volts, and then if we can just examine our signal down here, and we'll bring it back up to the 0 in the middle, and then we will change our vertical divisions to find our AC signal. This AC signal that we see is because our DC power supply is powered by a wall outlet, which is 60 hertz from PG&E. So we can trigger this signal to get a better understanding of where our signal varies between, and that will be our noise of our signal. So make sure your trigger is triggering off the correct source. So right now it's off source 2, but we want to go to source 1. So we change that, and then we can trigger our signal, which is given by this line, and the exact trigger value is shown at level. So to get a better look at our signal, I'm going to reduce our time scale by adjusting this scale knob right here. And we see this signal. So this is the AC noise that's running on top of our DC signal, which is approximately around like 60 millivolts, and we're measuring from here to here. So if you measure your signal later on, that kind of gives you an error bar. So to see where the oscilloscope really shines, we're going to hook it up to the arbitrary function generator, which we'll talk about later. But what's happening right now is we're inputting a sine wave that's 1 volt peak to peak and at 1 kilohertz. And we can visually see the change in voltage in the oscilloscope. So to take measurements with the oscilloscope, the nice thing about the digital oscilloscope is a lot of the times we don't have to actually sit there and count all the divisions, and especially if you have a changing signal, because not all your circuits are steady as this sine wave generator. So what we're going to want to do is hit the measure button and then add measurement, and then this will give us a list of options for what measurements we want the machine to display for us. So the most common ones we're going to be looking at is peak to peak, amplitude, max, min, or high and low. So starting at peak to peak, peak to peak tells us that we're going to measure from the bottom of the signal to the top. So since this is a pretty good sine wave, it's going to look very similar to amplitude, which measures from the bottom to top as well. However, if this is a noisy signal, say there's like a spike here or a spike down there, peak to peak will take the bottom of the spike to the top of the spike, whereas amplitude will ignore most of the spikes and just give you the signal of the wave. And similarly, max and min will do the same thing, except it'll only look at the max or the min, or high would be without the spikes, and same with low. Low would be without the spikes. So I'm going to add peak to peak and amplitude to our measurement. So I already added peak to peak, but I'll show you how to do amplitude. So you would use the multi-purpose A knob here, and you would scroll over to the option you want, and then you will hit OK, add measurement. And then we can clear off the menu by hitting menu off and hit it again, and then here we go. Measurement 1 is peak to peak, which is giving us about 1 volt, and amplitude is also about 1 volt. So if we notice here, the peak to peak measurement seems to be varying a lot more than the amplitude measurement, because, like I said before, the peak to peak will give you the active reading of all the spikes and noise that the signal carries, whereas amplitude is kind of negating all of those. So amplitude is very steady, whereas peak to peak, even with the arbitrary waveform generator, is still showing some variations. Another advantage of the digital oscilloscope is its ability to average a signal. So if you're taking a measurement of a signal and it's very noisy, such as this one, and there's absolutely nothing you can do to clean up that signal, and you know it, and you know that it's a constant period and it's triggered well, and you can see that it's not changing with over time, you can do something called averaging, which will take the average voltage of each spot and condense it down to the trace. So you can do that by going to acquire and then average, hit the button, go to average on, and here you can say how many averages per second you want to do. So you can increase the average to a very high number, which means every second right now is averaging 512 times. Whereas if you bring it lower, then it's going to change a lot more and have a more active signal. So if we increase our average really high, we can see that there's this wave that was buried in noise before. So you have to be careful when doing this, because if there's a varying signal and it's changing or it's fluctuating and you don't know if it's going to display a sine wave and you go average it, or you forget to turn it off, it's going to display a signal that's not accurate. It's a false signal. So in order to refresh the averaging, in case you come across something like that, say you changed it in your circuit, you can simply just adjust your scale and change it back in either one of the horizontal or vertical knobs, and then it'll kind of refresh and then take the averages again over time.